Hey guys, this is 6.4 notes. We were talking about compound interest and then growth and decay. I apologize ahead of time. I forgot my camera at home. I didn't have a chance to record the video in school today, so you get me without my lovely, happy, smiling face this afternoon or this evening. Anyway, so jumping into what we're talking about today, first and foremost, we're going to talk about something called compound interest, which realistically, actually, of this whole, I would say this whole chapter, this is the thing that you will probably use the most outside in the real world, regardless of what your application, like what job you're going into, what field of study you're going into, because this is all about interest. Our savings account have interest, our credit cards have interests, our loans, student loans, mortgages, all of that thing, they either give you or charge interest, and this is how we compound it, depending on what the rates are and all that other stuff. So compound interest follows this very, very complicated looking formula that boils down into 4 different variables. Our total balance, we use the letter A for the amount of our amount of money in the account. We use the letter P, capital P here, for the principal amount, which is kind of like that initial amount. How much you start with is the principal. Well, I'll even note that here. It's our initial amount or investment, depending on how it's phrased. Investment. Or I guess not necessarily how it's phrased, but what the scenario is that you're dealing with. Our annual interest rate is lowercase r, interest rate. That's going to be in decimal form, which I'll talk about in a second. And then the other 2 variables, actually, 5 variables, I guess, technically. We just use A for the amount at the end. But the 4 variables that determine what that amount is. N is the number of compoundings per year, and then T is time, is number of years. So going back to our R value having to be in what we call decimal form. So this is going to be given to us, it could be given to us in a couple different ways. We know, like if we were given something like 2/3, we know how to convert that into decimal form. Like if you get a 2 out of 3 on your homework assignment, that is, when I divide those two, 0.66 repeated, which tells you that you got a 66% on that homework assignment, if you got a 2 out of 3. That is how we convert back and forth between our decimals and our percentages. Because we could be given either of them. It could be given to us in decimal form, or it could be given to us in percentage form, which is the more common way of getting information presented to us. So how we convert back and forth is just by moving that decimal place. You can see I went from 0.66. I moved my decimal place 2 spots to the right, and that gave me 66%. So if I was working the other way around, if I told you that you got a 53% on a quiz or a test, let's hope that doesn't happen, but if you wanted to convert that into decimal form, you would just have to take this decimal, that's right after the 3, and move it to the left 2 spots to get 0.53. That would be 53% as a decimal. Or something a little bit more complicated, I suppose. If you got a 7% on something, or I was giving you 7%, to move it 2 decimal places to the left, I can move it 1 on the other side of the 7, but then I still need to move it 1 more to right here. So I actually need to add a 0 in front, because this as a decimal is 0.07. That's how I would write 7%. The other piece of information that probably might be a little bit cloudy to you still, number of compoundings per year. So when you're given interest on an account, or when they charge you interest on like a credit card or a loan or a car payment or anything like that, the number of times that it's compounded just means how many times a year they calculate how much interest you either owe or are given. It could be monthly, it could be yearly, just once a year. It could be daily. There's a lot of different ways that they can compound them, or times that they can compound them. Just know that the more number of times they compound it per year, in general, means you're going to get more money, because they're charging you, they're either giving you interest or charging you interest, which then they add that number into your account. All right, so let's go ahead and just plug one of these in. Let's do a little application here. For example A, we're asked to find the account balance after 20 years if $100 is placed into an account that pays 1.2% interest compounded twice a month. So what I like to do, the four things that we need in order to be able to find what that account balance is, we need P, R, N, T. So we need print, basically. We need our principal amount, we need our rate, we need our number of compoundings, and we need how many years, what time length it's going to be in. So in our description, we are told that it's going to be in there for 20 years. So that is going to be our length of time, how many years. So 20 should be our T. $100 is that initial investment. So that's going to be our principal. That's our P value. Again, that principal amount is our initial amount, our starting value. Our interest rate, which I'm going to highlight here in red, is 1.2%. Now again, we have to make sure we convert that into a decimal, so I have to move that decimal from between 1 and 2 spots to the left. So I should end up with 0.012. Should be our rate as a decimal. 1.2% is 0.012 as a decimal. Our last one is a little trickier, I suppose, We're told that our interest is compounded twice a month. So our N value is how many times a year our interest is compounded. So if it happens twice a month, we should know that there's 12 months in a year. If it happens twice a month, 2 times 12 should give me 24. So 24 times a year, my interest is compounded over the course of 20 years. So from here, I'm just plugging in those four values into my equation. So my amount in the account is equal to our principal, which is 100, times. That 1 is always there. 1 plus my rate, which is 0.012, over our number of compoundings, which is 24, to the N, which again is 24, times T, which was 20, power. So that's substituting everything in. From here, it becomes a giant order of operations problem. What we should be doing for our order of operations, I would simplify each kind of independent thing first. So like I would, on my calculator, I would do 24 times 20 to get that exponent, which should be 480. And then to get my parenthesis, I have to do that really first. I just do 480 just as a little side note before I actually jump in here. The way that I'm going to do inside my parenthesis, I'm going to do my 0.012 divided by 24. I'll get that on my calculator. I'll hit answer. I'll then add 1, so plus 1. And then I go ahead and apply that exponent of 480. So I raise that number to the 480th power. I would multiply by 100 last. And in this case, I should end up with $127.12. Because in this case, since I'm working with money, I should be rounding to 2 decimal places. Now let's take a look at that real quick. I'll pull up my calculator just so I can show you the process that looks like on my end, how I would usually do this. So again, I'm going to go ahead and do 0.012 divided by 24. It equals, I get 0.0005. I'll then go ahead and add 1. So 1.0005 is what's inside that parenthesis. I'm going to go ahead and raise that to the 480th power. That gives me that really, really long decimal times 100. And you can see 127.11729 is what I end up with. So when I round that to 2 decimal places, 127.12. 127.12. So it takes a lot of experience. The more you do them, the easier they become. And it's the same general process. There's some of us who might be able to plug that directly into your calculator, which is awesome. Good. That's awesome. Some of us might need to kind of take it one step at a time and deal with them as independent terms. All right, for example B, we're going to be comparing two different options. So this is going to be comparing how often we compound our interest. So if we are given $350,000 to be invested at 5% per year, we're trying, and we're going to be investing it for 10 years in total. We're comparing these two different options. If one account compounds quarterly and one account compounds monthly. Now, looking at our information, a lot of our equation is the same. This $350,000 is our principal investment. We know that 5% is going to be my R value, and in this case, that should be 0.05 if I put that as a decimal. And then our T is going to be 10 years. Right, 10 is going to be my T. Now, the N is the one thing that differs between these two different options. In part A, quarterly, meaning like as in 4 quarters, the quarter of the year, is 4 times per year. So every 3 months, basically, what that equates to. So 4 times per year is quarterly. Monthly, a little more straightforward. We know that there's 12 months in a year, so that means 12 times during the year it's compounded. So if I go ahead and start evaluating some of these, I'm going to do this left one here in red. So A equals 350,000 times 1 plus 0.05 over 4 to the 4 times 10 power. I'll go ahead and, again, do that same process on my calculator. I'm going to do 0.05 divided by 4, add 1, raise that to the 40th power, because we can see 4 times 10 is 40, and then multiply that by 350,000. And I should end up with $575,266.81 for that quarterly option. I'm going to do this next one in green. If I do part B, 350,000 times 1 plus 0.05 divided by 12 to the 12 times 10 power. So again, I'll grab my calculator, and maybe I'll do this one as an example. Where'd my calculator go? So for part B, again, I'm going to do 0.05 divided by 12, add 1, raise that to the, in this case, 120th power, and then multiply by 350,000. And now I end up with $453.32. So I end up with $576,453.32. So we can see just by changing how often it's compounded, we earn an extra $1,000 plus $1,200 just by, instead of compounding that same 5% 4 times per year versus 12 times a year. All right, shifting gears into our second idea here, which is exponential growth versus exponential decay. In 6.3 yesterday and last week, we looked at exponentials that had our different bases, and we determined that when my base was bigger than 1, we should use 0, 1, and 2 to evaluate points, and when my base was between 0 and 1, I should be using 0, -1, and -2 to evaluate our points. Now, without really putting fancy names to them, we really identified our exponential growth versus exponential decay. In those situations where my B value was greater than 1, where we were using 0, 1, and 2, that was exponential growth. When my B value, when my base was between 0 and 1, so when we had those fractions, that is exponential decay, because we used 0, -1, and -2. Now, the reason we call it growth and decay is because when our base is bigger than 1, our values are growing, right? When we looked at our graph, the points, the graph itself was getting further away from the asymptote as you move to the right in exponential growth. And exponential decay means those y values are getting smaller. So this was kind of going back to our general form of an exponential, y equals a times b to the x power. Here we just define x and y as our final amount and then our time or number of trials. In a word problem, our a and our b values, our a is that initial amount, which again we talked about yesterday. That a value is always that distance from your asymptote up to your y-intercept. But here it's going to be your starting value, your initial amount, kind of like that principal we were just talking about up above. And then our b value, our base, of course, is our multiplier. But here it's our growth or our decay factor. It's how fast things grow or how slowly or how fast they decay. So in example D here, we are reading a novel where an entire 40-player baseball team becomes zombies. It is predicted that the number of zombies will triple each day, and we're asked to predict how many zombies there will be after a week. So we can see again, we need 2 things really. 3, I guess, if you're evaluating all the way. 2 to write the equation, 3 to evaluate all the way. We are told there are 40 players in the baseball team. That would be our initial amount. That's our A value. We are told that the number will triple each day. That's going to be our growth rate, our growth factor. That's going to be our B value, which is going to be positive 3, right? And multiplying by 3 each day. A value is 40. And then our X is a week, right? That's the time or the number of trials is going to happen. So here our X is going to be positive 7. So I just throw all those things together in my equation. Y equals A times B to the X power. 40 equals 3 to the 7th. Sorry, 40 times 3 to the 7th. So grab your calculator. 3 to the 7th power should be what I'm doing first, which 3 to the 7th is 2,187. So then 40 times 2187 gives me 87,480 zombies in this scenario. Which, that seems really easy because we had a very, very nice B value. We just were tripling, or, those kind of things are easy because, like, if we even think back to our pay it forward activity or way back to our penny a day, those multiplications were easy because we were just doubling our money, or we were tripling the number of people who have gotten good deeds helped to them. But that's not always going to be the case. And actually, more than likely, when we're dealing with exponential growth or decay, it's going to be some percentage change where it's not a nice, clean number. And when we're dealing with something like that, we have kind of an alternative equation that we can use. So if you're given a decay rate, if you're given a percentage change for what we're dealing with, instead of just a multiplier, a growth factor, you could use this equation instead. So it's still my initial amount P, it's still my time variable T for how long that's happening for, and then R is still my my growth or decay rate. Now here we're dealing with exponential decay because in this scenario that we're about to read through, we're losing value. So that's why we're using decay. But the growth equation is set up very similar, except that now in growth we're going to be adding instead of subtracting. So reading through our problem here real quick, if we buy a used car, which I don't know what kind of used cars cost $18,000, but sure, we buy a car that is worth $18,000. The value of the car will be less each year because of something called depreciation, which hopefully you guys know about. Cars and different things depreciate, they lose value at a certain rate just because of them being older, newer models being replaced by them, so on and so forth, many different reasons. But cars depreciate at an average rate of 12% a year, which is pretty accurate, depending on how old the car is and how desirable the model is. So we're asked to write an exponential decay model that represents the situation that is used to estimate the value of the car in 8 years. So if we buy a car today for $18,000, it depreciates 12% a year in 8 years. Maybe once we pay it off, if that's the length of our loan, we're looking to see how much it's going to be worth in 8 years. So some things to look at. We've got kind of 3 different numbers in our problem. And hey, look, we need 3 different numbers to figure out our equation. We need our P, our R, and our T. So our principal, our P value, is still that initial investment, that initial value. R is still my rate, my change, which again here, this is going to be, 12% is 0.12 as a decimal. And then of course my time value is going to be 8 because that's how long we're leaving it in there for. So if I put all those things together, A equals 18,000 times 1 minus 0.12 to the 8th power, which is 18,000, 0.88 to the 8th, and then I can go ahead and grab my calculator and evaluate from there. Now, this little piece here, before I give the answer, after I do that subtraction, 1 minus my R value, that's what we call the decay factor, because that is what we're multiplying by, right? That's what we're multiplying by each step of the way is 88%. That's telling us that we're maintaining 88% of our value. So from year to year, our car is only worth 88% of what it was worth last year. If you go through and evaluate this on your calculator, 0.88 to the 8th power times 18,000 tells us that after 8 years, our car is now only worth $6,473.42. What a sad life we live, but that's what it is. All right. Last but not least, we have a exponential growth problem with our percentage change instead of a growth factor. In this situation, our train is going downhill at 140 miles an hour. Suddenly the brake system fails and the train begins picking up speed, going 11% faster each minute. How fast will the train be going? In a total of 5 minutes. So once again, I'm looking for the same 3 variables. We need that principal amount, that starting value. We need the percentage rate that we are changing at as a decimal. And then we need the length of time, our T value here, as well. So, hey, look at that. I see 3 different numbers. Those are going to be my 3 values. Our starting speed in this case, that's going to be our principal. That looks like a D. Let's try that again. Our starting speed is our principal amount. Our percentage change is R, is 0.11. And then T is 5 in this case because our train is traveling for 5 minutes. So the difference between growth and decay, if you notice, my 2 formulas are very, very similar, except that in growth, I'm now adding my R value. I'm adding a percentage to 1. In decay, I'm subtracting from 1. That's just because, again, in growth, I'm gaining. In decay, I'm losing. So my formula, when I start plugging this stuff in, 140 times 1 plus 0.11 to the 5th power. So 140 times 1.11 to the 5th. Again, this, after I add 1 plus my R value, has a special name. This is my growth factor. Again, that's just how much my speed is going to be in comparison to the previous minute. So it's 111% of what the previous speed would be, which makes sense because, again, we're gaining value. So we keep 100% of the speed from the last minute and then gain an additional 11%. Once I evaluate, I should end up with 235 miles an hour, specifically 235.91 miles per hour. All right. That is all I got for you for today. Your homework, which is up there on the screen, page 319 and 320, 6 through 32, just the evens. As always, if you guys have any questions, concerns, thoughts, ideas, hopes, or dreams, make sure you guys are reaching out and letting us know. Otherwise, have a fantastic day. We'll see you soon.